Hi, so in this chapter, we'll start to talk about sensor fusion and specifically how we can use our magnetic compass to improve our pose estimations. Before we dig into sensor fusion, though, we'll first talk about sources of noise, why we can't sort of expect what we're doing so far to work, sensor calibration, and signal smoothing. Those are all topics that'll just take a slide each and won't take a lot of our time to cover. I'll then discuss sensor fusion at a high level, and then we'll look at our very specific case here of using odometry and adding in compass information so that we can correct for problems that arise with just using odometry by itself. To talk about sensor fusion and sources of noise and camera and calibration, it will make sense for me to take one quick step back and talk about the pipeline of how we process data on our robot. The first step is the sensing step. And you can think of this as the data collection. The data collection step, and we've already done this. This includes the wheel encoder data and processing that. And we'll add to it our compass, along with other sensor information going forward. And I really shouldn't say, and it includes the processing step, because that's really the perceive part. So we could call that the processing step, or the interpretation step. And a lot of times you'll see those two steps combined, and you'll just hear this process called sense, plan, act. It makes sense to try to break those out as two separate steps because there's some things that we can do in between them. But I should round out talking about perceiving with mentioning odometry and pose estimation. So we can collect our data, and we could do some pre-processing to it at that stage that doesn't necessarily have to do with perceiving or interpretation. For example, we could smooth the signal to get rid of some of the noise associated with it, which can come from a variety of sources, and we'll talk about those on the next slide. The step after perception is to plan. And we have not done any complex planning yet, but you can think of this as something like path planning. If I were to give you a map of Edmonds and tell you that your robot starts at some specific room, you could then use that map of Edmonds and plan a path from your starting location to some other location in the building. And to drive yourself to that goal, you would need both of these sense and perception steps. You would need to estimate your pose so that you know, okay, I started out here, after 10 seconds I'm now here, and now I need to turn right so that I can move into the room in which I'm being directed. And speaking of moving into the room in which you're directed, that would be the act step. So you can think of this as the control part of the process. So that can be low-level motor control, but it'll also include higher level things like position control. And as you might imagine, it's really hard to act and plan if you don't have good data to begin with. So let's now talk about some of the sources of bad data. These will probably be the things you're most comfortable with from this subject. Things like mechanical wear. You could think of like the tread on your tires as changing the behavior of your vehicle. Or for your robots, as the motor brackets get a little bit loose from the chassis, they'll be directed at a slightly different angle. We would also have measuring inaccuracies. So that could be as simple as you think your wheel is 7 centimeters in diameter, but it's actually 7.1, and you just didn't take the ruler close enough to your wheel. That's going to make a big difference in odometry, especially over longer periods of time. The wheels are laser cut, so those will be fairly accurate measurements, but one pretty good source of inaccuracy would be the distance between the two wheels. So the track width, that distance between those two wheels. And it sort of depends on how hard you've pushed your wheels on or how softly you've pushed your wheels on. And you could be off by as much as, half a centimeter pretty easily. Another source of error would be fabrication inaccuracies. So, for example, the wheels that we provided might not be tight enough on the axle, so you have a little bit of a wobble. That's definitely going to cause your robot to end up in a slightly different position than we thought. But in addition to the mechanical problems for fabrication axles, inaccuracies or issues, this can also be mechanical, but also electrical. Which will start making a bigger difference this week since we're adding another sensor. And this sensor that we're adding, the compass, is particularly susceptible to being off due to any sort of electrical signals that are next to it. So that could be just the current flowing through the wires, you having your hand too close to the compass, or having the compass too close to the motors, for example. All those things are going to cause inaccuracies in the compass, along with just having bad transmissions, so if the wire is loose, for example. And I really combined these two. I should have left this as a second one, but poor electromechanical design. Like I said, not having a shielded magnetic compass is going to be another source of noise, along with just having cheap magnetic compasses. The ones that we're using are less than $1 a piece, and so you get what you pay for. They're just going to have inaccurate data being produced from them. Just from having poor quality components, which have noisy electrical characteristics, and low bit depth. So we're not going to be using a 64-bit integer to receive data from the compass, for example. It'll be lower resolution than that. And in addition to sources, I should talk a little bit about the types of noise that you might see. Most of the noise we will see is just random noise. So if your true signal looks something like this on a time plot, then maybe what we're actually measuring looks something more like this, and maybe a spike every once in a while. But for the most part, your signal is near what it's expected to be. You might also have drift. Certain types of electrical sensors will just exhibit drift. So your signal will sort of wander, and it might wander back. But not necessarily tied to any physical characteristics. It's just not always hovering around the true signal. And a final one that I'll discuss here would be bias. So if our true signal is the green signal, we might end up something like this purple signal, where we just always have some constant offset. Maybe we also have that random noise, but now it also is accompanied by this random offset. And that offset might depend on what angle you're facing for the compass. So maybe sometimes that bias is 0, and sometimes that bias is higher. And so we'll talk about technique called exponential moving average that'll mostly handle these types of errors, but not so much the bias type. For the bias type, we'll look at a different process called calibration. So there's a general process for calibrating any of your sensors. The first step is just to repeat a bunch of experiments. And you're going to repeat experiments with different configurations. So if we put our compass down on a table and we face it in one direction, we'll collect some data for some amount of time, and then we'll want to rotate our compass around and have it face a different direction and have it record data over another amount of time. So the key here is in this first step to put the device into a known configuration. So heading directly north, or heading directly toward the door, or whatever is sort of important for the task at hand and the sensor you're trying to calibrate. The second step is to record your data. And of course you'll repeat that for different configurations. Like I said, pointing north, pointing 30 degrees, counterclockwise, and then every 30 degrees until you're back facing the original direction. And then probably doing that process multiple times so you can compare one set of results to another. Your process after that is to compute some summary statistics. Things like the mean and the average. And if you're lucky and those values are low enough to be within your requirements, maybe we require our robot to be able to get to a point within 10 centimeters of accuracy. And with the results that we're given here in some simulations, we're almost always within that 10 centimeters of distance away from the goal. So if you're done at that stage, you can really just use your device as is. However, more than likely, you'll need to complete a third step, which is to update your model parameters. So you have to update your parameters to fit the data. And the word model here sounds fancy, but we've already seen several different types of models. So for example, we have a model that gives us the linear velocity and the angular velocity of our robot. And those are based on the speed of the left and right wheels. Well, if you recall, these values for VL and VR, those are dependent upon a couple of metrics. So for example, VL depends on phi dot L times the radius. And so maybe that radius is one of the parameters that we need to tune or fit. So in our code, in our simulation, we'll keep trying different values of R until our simulation matches our real-world results. And then we'll hope that that carries over into our actual device. So as a couple of examples, we could use our odometry example, rotate the compass around, fit the data, and maybe we have to do some correction when the device is heading directly north, and then a little bit less of a correction when it's pointing directly south. And so we would have essentially a function that we take the raw data from, pass it to that function, and then it spits out our corrected value. And same thing for the robot's odometry, like I just mentioned here. We have certain parameters, the value for R and the value for L. We can tweak those in our simulation such that our simulation matches the data that we've generated. So that handles the problem with certain types of noise, but really just noise in general. You're almost better off using not the raw values, but instead a smoothed out value. So I'll come up with a pretty boring example here of a sinusoid. So let's say that we have a pure sinusoid, looks something like this. Well, if we're measuring that data, maybe that sinusoid is being generated by us rotating our compass around in a certain pattern. The data we're actually going to read is going to look something a lot more like this. It could also have some sort of vertical offset if we have a bias. It could have some sort of horizontal offset if we have a different type of bias. Both of those would be sort of a constant or fixed value. We could also have something that sort of clips out towards the top, like rounds out the top and rounds out the bottom, but then does pretty well at certain angles. And depending on the data we get during the calibration process, we might have to do something to our signal before we perform this smoothing process. But smoothing is going to be essentially what you're picturing by just the word smoothing. If our signal is noisy like this, the value we're going to send out is going to look more like this. Just a smoothed out version. And the exact version of the smooth signal is going to depend on a smoothing factor that we'll have. So typically what we'll use is something called an exponential moving average. And this is something used in a lot of different places. It's actually used as part of most gradient descent algorithms when you're training a neural network, for example. And it's a simple process. If you have a signal y, and we'll say we have y at time step k, we'll say that those are just measurements from our sensor. So maybe that's this plot above, measured at these different time points. Our smoothed out version is going to be whatever our current measurement is. It'd be strange if we were taking measurements and then not using them, multiplied by some factor, plus the previous time steps value. So you can think of the value of alpha as a weight. It's a weight for how important we deem the past values. So the higher the value for alpha, in the way that I've written the equation here, the higher value for alpha, the less important we're considering these past values. We would be taking 1 minus some large value like 0.9, which means we wouldn't be weighting this very much. And most of what yk is, y hat k, it's just based on our current sample, our current measurement. However, if we're finding that our signal is really noisy, maybe we'll use something like 0.5 for alpha, in which case we'll take our current value, multiply it by half, and then take our previous value and multiply it by half. So it's basically saying we're giving equal weight to our current sample and our previous sample. And that'll have the effect of smoothing out the value we have here. And in fact, if you were to unroll this equation a couple of steps, so by that I mean, if I were to look at y of k, we say that's dependent upon the current measurement. And I'm missing a hat here. Plus 1 minus alpha times the previous measurement. But the previous measurement just follows this same equation recursively. So for that previous measurement, I could say y of k minus 1 is really equal to alpha times the previous measurement plus 1 minus alpha times the previous estimate. So the point I'm trying to make by unrolling this another step is to say that the current value that we're going to plot is based on the current measurement the previous measurement, and then also the previous estimate. So depending on your value for alpha, that gives you basically an idea of how far back for a given point, how many points back in the history are you taking into account. So if alpha actually is 0.5, you'd be looking at a lot of the points back in the past. And so what you'll find is some sort of like delayed shift. And so you can have too much smoothing essentially. And as part of this week's chapter, I have a little tool here for helping you play around with exponential moving average and getting a better feeling for what I just mentioned. So for example, this black line underneath the yellow one is the true signal. So we could change its amplitude, we can change its frequency, along with its phase and offset. We can also add some noise to the signal. And without any smoothing, the orange line here completely follows the black line. If we completely smooth it out, we basically just get an average of the entire history of the signal. So it looks like the average of this is a little over 1, and that would be due to the offset that I've got here. And the high level of noise. If I were to add a little bit of too much smoothing, you'll see this delayed effect that I'm talking about. The orange line is sort of shifted to the right from the black line. But as I reduce the amount of smoothing, we get to a point here where the orange line's still pretty noisy, but it's less noisy than the black line. And then at some point, there was no point in having any exponential smoothing at all. It's just basically the same signal. And so for part of this week's exercise, I'll have you play around with that and show me good values that you found for the value for smoothing. All right, so after calibration and smoothing, we can do something called sensor fusion. And sensor fusion really is a simple process, a fancy name for just saying we're combining multiple data sources. As a way to generate a better estimate. So a better estimate of some value. So that value could be what direction am I heading, where is my pose in this three-dimensional configuration space, so my x value, my y value, and my heading. Or it could be something that we're not talking about in this particular class. So for example, what is my distance to the stop sign ahead? So I would need an estimate of where I am and where that stop sign is to get the distance. And there are multiple sources of information for that you can use for your data sources. So common sources would be your sensors, but also models. So you could have, for example, a model of the airspeed for a drone. And if you have a model for the airspeed and you punch in the wind that day, you don't even need to have a sensor on your device to tell you how much it's going to push you off course. But it can still be a useful source of information for planning algorithms, for example. So pretty obvious, I think. But the benefits here of doing sensor fusion is you have an increased quality of data. So by this data, I'm talking about sort of the output data, like, for example, your pose. You have more reliability. If you're working on an autonomous vehicle, you don't want to depend on a single sensor to tell you how far away from a pedestrian you are. Hopefully that goes without saying. You can also estimate things that are not directly measured. So much like we have binocular vision, two eyes, you could have two cameras on your robot, and then measure and use those two separate sensors, fuse them together to get something like a distance to a target. There's an entire class of algorithms called structure from motion, essentially, where you can do that sort of triangulation. And of course, increased coverage. We do have LiDAR sensors for our robots. That's just going to be a simple forward-facing array of 8 values, or 64, depending what mode we put it in. But you can imagine you won't be able to see something coming up from behind you with that sensor. So you could have one forward-facing, fuse that with data from a rear-facing one, and have a better idea of the entire space around your robot. And there are a lot of reasons why, for our device, it might be better to have multiple versions of each of these sensors. So for example, if I put a compass on one spot of our chassis and a compass on another spot of our chassis, maybe one of them has a little bit of drift when you're facing forward, but the other one's pretty solid. And as the robot turns around, maybe one of the sensors has less interference from, for example, a motor being right next to it compared to the other one. So as we rotate to the right, maybe when we're facing, I'll call that east. Maybe when you're facing east, this sensor picks that up better than another sensor. On the other hand, having multiple sensors doesn't always give you better data. You could have what's called correlated noise. Which is exactly what it sounds like. Maybe both sensors are experiencing the same effect from having motors near them, and so they both have sort of weak spots or blind spots. So a lot of times when you're doing sensor fusion, you want to use different types of sensors, like we are for this class. We're using the wheel encoders and the magnetic compass. And we actually have inertial measurement units too, which I'm now adding as a sort of optional part near the end of the class instead of requiring it from everybody. But having multiple sources of information that collect data in different ways, so using a magnetic field or using a MEMS gyroscope, for example, or accelerometer, having those different sensor modalities is going to improve your results. Something else that'll improve the results is using a proper sensor fusion technique. For anybody that's curious, I would point you in the direction of doing a little bit of reading on what are called Kalman filters, or particle filters. We won't have time to discuss them in this class. Instead, we're going to use an extremely sort of primitive version of sensor fusion. But, like I said, for those interested, those would be techniques you can apply to a lot of different domains, and well worth taking a chance to look at. But for us, we'll be focusing on a really simple method of improving our pose estimation. So, as a reminder, our robot is driving around in this two-dimensional flat world. And our robot has 3 components to its pose. Our robot will have its defined center of mass, and it'll have its x-coordinate and its y-coordinate, and then its heading. Those are all part of our robot's pose. And currently we're writing out that pose by just saying if it starts at the origin, facing along one of these 2 directions, usually the x direction, it gets to this other location by driving its 2 wheels. And we have no way to detect if the wheels have slipped or not. And if they've slipped, we're just going to have a poor estimate of our robot's pose. A little bit of slippage is not going to cause a large change in the robot's displacement from the origin. And by displacement, I'm really talking about this value here. So how far away from the origin it is. However, a little bit of slippage can cause a pretty good change in our heading angle. And it can cause a pretty good change in what our final XY coordinates are. So again, not necessarily in displacement, but in final XY coordinates. And it's not hard to imagine why. If I show you a scenario here of saying the robot starts here, let's say here at point A, and in one scenario it's heading directly along the y-axis for 10 seconds, and it gets here to B, and let's say that our sensor readings were a little bit off, and it was actually facing more like in this direction, and we can call that one B prime. So these two distances are going to be pretty similar. However, the final locations can be quite a bit off, and the longer we run this, the more these two locations diverge. And again, the problem here is that angle error, the angle error that we have between those two. And that's exactly why we're bringing in a second value for that angle, that heading, a compass. Something that measures an external value, not just the internal sensors like we have for the encoders. And we'll be doing what's called like a simple weighted fusion. So our value for the heading is going to be equal to the value we're getting from the kinematics plus the value we're getting from the compass. And we need some way to weight the importance of those two values. And so we'll use a value called alpha. And we'll multiply one of these values by alpha and the other by 1 minus alpha. And as long as alpha is in this range 0 to 1, we'll end up with a pretty good estimate, or a range of possible good estimates. So if alpha is shifted all the way to 1, that means we're only looking at our kinematics value. If alpha is shifted all the way to 0, it means we're only taking values from the compass. And anything in between, we're sort of equally weighting them. Or not equally, but weighting them in some way. 0.5 would be an equal weighting. Something else I should mention is this value from the compass is actually going to be an estimated value. It's going to be the exponential moving average of our compass value. So that's what you'll be doing this week, and the second part of the exercise is essentially coding up this equation as it is here. And again, on the course website, I've added another little simulation here, which lets us randomly simulate the robot with different values for example, the compass noise. If our compass is really noisy, you can see how that has an impact on things. And if we decide to not use the compass at all, rather this one, if we decide not to use the compass at all, you'll see the impact of that. And generally, even with a really noisy compass, we're going to end up with better results than if we got rid of the compass entirely. Alright, that's where I'll wrap up this video for this chapter. Enjoy doing some sensor fusion.